Good day. I'm J Wildberger. Today we're going to see how some of the foundational issues that we've been developing for geometry relate to primary school mathematics education. Geometry is a lovely and important subject that young people should see more of. It's been unfortunately sadly neglected in the last few decades, and it's really time that geometry was brought back as an important, even an essential part of a young person's education. Let's start by emphasizing a few main points. I think the use of a graph paper, or what I call the grid plane, is a key point in making this subject more accessible and more clear to young people. It's also a great way of connecting the two subjects of arithmetic and geometry. These two naturally have lots of links, and a grid plane like this brings out those connections. Now, although this foundation series has been concentrating on the logical development really meant for higher mathematics, nevertheless there are some natural connections to primary school education. But it would be wrong to think that I'm suggesting that the logical treatment that we've been using so far, or developing, should be applied directly to primary school education. Rather, one should be aware of the goals and main ideas in developing curriculum for primary school. And I'm not going to be doing that today, just giving you a few random ideas. When we start with the grid plane, the first thing that strikes us, I suppose, is that it's divided up into a lot of little squares that we can call cells. And it's very easy for students to think of rectangles or squares as being created from these basic cells. This naturally connects with arithmetic, because after all, counting the number of cells or counting the area of a rectangle is naturally really a question of multiplication. And as the ancient Greeks realized, there are many other aspects of elementary algebra or arithmetic that connect naturally to geometrical pictures. For example, if you want to sum 1 plus 2 plus 3 plus 4, and perhaps carry on like that, then one natural way is to think of that sum as being this figure here. And if you take another copy of it and add it there, then you see that twice that sum, whatever it is this rectangle, showing us that 1 plus 2 plus 3 plus 4 is half of 4 times 5. And that's now a formula that students can remember because they can associate it with a picture like this. There's also some other fun things that one can do. One can talk about, for example, animals, configurations created from cells, and put adjacently like that. And it's natural, for example, to try to classify or count all the different animals of a certain size. We can create circles in a very precise way by the use of graph paper. And of course, we can talk about points and lines in a very explicit and direct way. So a line in this context is something that students can easily understand. There's a regular pattern going over 2, up 1, over 2, up 1 that determines a line. It makes it easy for us to talk about parallel lines as well as perpendicular lines. And there's no reason why young people can't be taught about the notion of a vector, which describes the relative position of 2 points. In the early years, there's no need to have a coordinate framework. We can just deal with the graph paper as it is and talk about the relative position of points. Of course, we can also talk about triangles as being half of rectangles, or more generally as being created from parallelograms by taking half of them. So there are many natural questions having to do with counting, having to do with areas, having to do with distances, and also in terms of paths. For example, one can count the number of paths from one corner to the opposite corner of a square or rectangle. It's a very interesting problem, which is naturally associated with all kinds of rich arithmetic. The number of paths here is 20. The number of paths from here to here, I'll let you check, is 10. When teaching young people geometry, it's important to be precise, logical, and concrete. A piece of graph paper helps us to achieve that. Instead of talking about parallel lines in this nebulous way as just 2 lines which don't meet if you extend them, in the grid context, it's very explicit. 2 lines are parallel if they have the same direction vectors. over 1 up 3. Over 1 up 3, therefore those two lines are parallel. And there's no need to talk about some indefinite extension that happens way up there. Instead of talking about some vague triangle like this, just drawing a triangle on a piece of paper, it doesn't specify the triangle very precisely. And the student could easily be forgiven for not being able to copy that triangle and not know exactly what you're talking about. When we work with triangles in the context of a piece of graph paper, then we know exactly what we're talking about. And it also makes it easier for students to both copy and to create diagrams that are realistic and meaningful. The grid paper is also great for talking about transformations, which are an important thing that young people should learn about, that we haven't talked about yet in this foundational series, but we're going to have to. For example, starting off with this shape here, we can reflect it in this line here to get this one. We can translate it to get this one here, and we can rotate it to get this thing here. So these kinds of transformations are easily describable in terms of the graph paper. A piece of graph paper is also very good to talk about areas of triangles, which is a subject that we also haven't yet talked about, but we will. So in this case here, you can see that this triangle here has an area that can be computed by cutting and pasting, by thinking about the area of that bigger rectangle and cutting out smaller right triangles whose areas we can compute exactly. That's a better way of thinking about area rather than base times height over 2. I'd like to emphasize also the importance of constructions and drawing in geometry. This is an aspect of the subject that goes back to Euclid and was very important to the ancient Greeks. Students should know how to, for example, construct the midpoint of a segment. The classical tool for doing that is a compass. And I think every primary school student should have a compass and should be comfortable using it. We draw a circle there, draw a circle there, we see where the circles intersect, we draw a line, there's the midpoint. Similarly, finding an altitude from a point to a line or a perpendicular. You compass there, make a circle, then you have 2 points, and then find the midpoint of that point. That gives you a perpendicular line. And then with these kinds of constructions under their belts, students can experience all kinds of beautiful triangle geometry experimentally. Without necessarily being able to prove them, they can, for example, see for themselves that the 3 medians of a triangle intersect in a point. That's something that every student should see. In terms of theorems and proof, there's one theorem at least that students should see a proof of, and that's Pythagoras' theorem. And the proof doesn't have to be and shouldn't be the algebraic one that I've presented, but rather a pictorial one. For example, the one that you can find in my wild trig series. In year 5 or 6, students should become familiar with coordinates, and they should at some point learn that the equations of a line is given by this kind of formula, y equals 3x minus 2. That's the simplest kind of formula for students to learn initially what a line is. Later on, they can learn the more fancy, sophisticated way that we've been talking about lines, but this is a good way to start. Also, I haven't talked too much about three-dimensional geometry, but students should be familiar with the basic shapes and also have some familiarity with Platonic solids. These are just some of the things that students should see, but I think it's unfortunate if young people do not get exposure to these important and classical and historical topics. Next time, we're going to talk about a notion which seems simple, but in fact is more subtle than it appears. It's the idea of an area, a fundamental concept for planar geometry. I hope you're going to join me for that. I'm J Wildberger, and thanks for listening.